Everybody, thanks for having me here. Given the time pressure for this talk, I'm going to be very brief and get to the meat as soon as possible. What I'm going to talk about is part of a work that I am doing with Alessandro Bravetti and Federico Zadra. And I'm assuming that you already know a lot about contact mechanics, so I will be very brief there. I will just use it to set up some notation. I will briefly discuss what are contact integrators, Hamiltonian and variational, what they look like, and then finally I will discuss a recent example that came from Cosmology, in which we study something that is different than usual. So in contact mechanics, we look at odd-dimensional systems that are endowed with a maximally non-integrable hyperplane field. This essentially means that we are looking at a space that is odd-dimensional, endowed with a special one form whose kernel defines this distribution on the tangent. In this case, we can assume everything is global, and we will use Q, P, and S as our variables. As in the Hamiltonian case, we can actually define an isomorphism between Hamiltonian and contact Hamiltonian vector fields. What in the Hamiltonian case would be our symplectic form, dp wedge dq, which gives the isomorphism from the contraction of the vector field has to be equal to minus the differential of the Hamiltonian, is translated in the contact system in a slightly different way. First of all, you have something similar. You have the contraction of your vector field with this contact form eta has to be equal minus h. And then you have something that gives the conservation of the contact form. We said that this distribution is the kernel of the contact form, so multiplying the contact form by a positive function, while a non-zero function is going to preserve this kernel. So all the transformation that act on it by doing a multiplication by a function are called contactomorphism. So we want this transformation to be a contactomorphism, and in particular we want this actually to project on the rep of our contact form, which is a vector field that is all along the contact form. When we look at the equation of motion for the vector field that we obtain with this construction, we find out that we get something that looks like an Hamiltonian system, what you see here in black, and some extra terms. Some extra terms that include some effect on the momentum. The derivative of the momentum now includes minus p dh in the s. So we see that if the Hamiltonian does not depend on the extra variable s, we are actually in the Hamiltonian case. And further, we get the new equation for the extra degree of freedom, this s, that if you look carefully is actually the Legendre transform. So it would be a Lagrangian somehow of our system. So you see there is the action in a differential terms. Now a big difference with the Hamiltonian system due to these extra terms appearing here is that energy is not conserved. So if we still think about h as our energy, then we look at the time derivative with respect to the flow, and we get that this is actually not necessarily zero. It's minus h dh in the s. So if this h does depend on s in a non-trivial way, then you get conservation of energy only in the special foliation h equals 0. As I mentioned, we seem to have some action principle here, so let's look also at the variational counterpart of this. If you take a differential equation that we had written there essentially s dot equal a Lagrangian in t, q, q dot, and s, then you can define a variational principle. This was done by Erglotz, and this essentially tells you that the curve is a critical point, so it's a solution for this variational principle if all the variation of this curve vanishing at the endpoints leave the endpoint s of t invariant. So in this case, we can get the Euler-Lagrange equations out of it, and you will notice that you get the original Euler-Lagrange equation, the usual one from the Hamiltonian system, plus an extra bit that have an effect due to the s attached to the momentum, the L in the q dot. Again, from here, or in fact already from this equation here, if the Lagrangian does not depend on the action S, then we get back to the Hamiltonian setting. But here, if we go and do the Legendre transform, we get back the corresponding contact Hamiltonian. So this is really the dual of the contact Hamiltonian that I was just describing, and we get the same law of conservation, in fact non-conservation of energy. Now this non-conservation is crucial. This the most studied example in the contact mechanics world is I think is the Rayleigh dissipation. It would be described by this Hamiltonian. It's a standard Hamiltonian plus a term that is linear in the action. Then when you look at the equation of motion, what you get this friction term here. If F is minus alpha and if V is just Q square alpha, for example, you would get the damped oscillator. And there are plenty of papers out there even just dealing with that. In fact, you can just extend the formalism that I was showing to include time, and this is relatively immediate, and the formalism allows to treat very general Hamiltonian of this form. Of course, you can treat other stuff like thermodynamical systems or even gradient flow as you would do in control theory. You just, instead of considering just the Hamiltonian that you get by augmenting the system, you do an extra projection over one of the fake momenta that you added, and you get Hamiltonians like the one on the form below that are actually useful to study oscillatory system with nonlinear oscillations. Our integrators, some of them are just for Hamiltonians of this form, and this will be contact Hamiltonian integrator for splitting. There will be a splitting integrator for Hamiltonian written as the split of this various part, and other would be able to deal with everything or more complicated system, and this would be the variational integrators in which the form of the Hamiltonian does not play such a big role. So for the contact Hamiltonian integrator, what happens is that if you have a splitting Hamiltonian, so an Hamiltonian that you can split in terms of many vector fields, a special composition of the flow of this vector field gives you a map. So you just compute the flow of each vector field individual, you compose them, and you find out that this special composition, as you see that it for the Hamiltonian systems, gives you a contact Hamiltonian integrator in the sense that this flow will preserve the contact form. The contactomorphism part is natural because this is just a composition of contactomorphism. And you can use the Baker-Campbell-Artus formula to compare the flow of the Hamiltonian system and see that this is actually giving something with an order of with an error of the order of tau square. Composing map of the second order allows you to construct higher order maps. This is actually quite useful and quite straightforward and comes with a very explicit modified Hamiltonian. Although it gets more and more expensive with very high order. As an example of a splitting Hamiltonian, you can see that the integrator that you get, which would be a combination of these three maps, say A, B, C, B, A, is a very simple explicit integrator. Something that is extremely simple to write and extremely fast to run. Similarly, you can start from the Herglok's principle, discretize it, get what a discrete curve should satisfy to be critical and solve the discrete Herglok principle, and then you find that this gives you a rather explicit way to compute discrete Euler-Lagrange form, and then from here, as you would do for a standard variational system, you can get an integrator. A very important point is that since our equation is in a differential form, we actually get a different type of equation from what you would get by using Lagrange-D'Alembert principle. And what you end up having is an integrator that is in general explicit, and which is explicit also in its time dependence. While if you use Lagrange-D'Alembert in general, you will have an implicit integrator with adaptive time step instead of having being able to use fixed time steps. I can't get into the details of that, but again, in this prototype Hamiltonian up here, where this f again does not have to be necessarily linearly dependent on s, you get immediately, in this case, a second order discretization. So you get immediately a discrete Lagrangian, and then computing the discrete Euler-Lagrange equation and equating the right term, you get the integrator that you see here in the picture. Again, something that you can write extremely easily and apply in a quite straightforward manner. So let's go then to the example in cosmology. We have these classes of integrator. They have been applied to many systems in cosmology, but in all systems that had some sort of friction. Even in the case of the line-ended equation that described the density of stars, we had a term that resembled a sort of friction. So we could use the integrator for the linear Hamiltonian. There was not some new phenomenon appearing. Now we want to look at the works of David Sloan and more recently of David Sloan and Sean Grebe, and even some past work from his collaborators, in which they discuss Friedman-Lemaitre work at space-time and Bianchi models in cosmology. What happens is that there is a singularity there that depends on the scale, the change of scale in your system, but the space-time is actually scale invariance, and this scale invariance can be seen in terms of contact geometry. So when you do a reduction that gets rid of the scale invariance, you in fact are doing a projection to a contact system that leaves you with an Hamiltonian of the form that is written there. The potential will be a bit complicated, and S square will have non-trivial meaning in terms of cosmology, but all in all, you have a rather simple contact Hamiltonian system coming out of here. And the important point is that there's this quadratic dependence on the action. And this quadratic dependence makes a big difference, because changing sign there allows to have cycles, sinks, sources, and whatnot in the system. So this has the chance to be an interesting system to study. And the remark in those papers is that by having a scale invariant description of your system in which the scale factors just disappeared, you've got rid of the singularity. So you can actually study what happened through the Big Bang, what different things happen, and so on and so forth. So this is a work that has just started, and there is surely still a lot to be done. Right now we are just going to investigate what a simplified system look like. So we take an harmonic oscillator now, simple potential, with this quadratic dependence on the action. And we shift it a bit to have that the zero level set is a nice ellipsoid in space. In fact, this gamma is just a sphere in space. And we look at what kinds of system we have, and then we look at what our integrators give when you study motion on this system, and how they compare to for example, a higher order integrator of fixed time step like Runge-Kutta, which is not geometric. So in this case, we have this nice invariant surface at h equals 0, say gamma equal 1 is a sphere. This comes with an invariance of manifold on this line, and everything else is 0, where the north pole on the sphere is an attractive fixed point, so everything here will go down there. And this point here is a repeller, so everything here will be thrown away. Now what is interesting is that this repeller here is very unstable. Stuff goes out exponentially fast out of here. And since this one is the attractive guy, what happens is that you are thrown out here, you will go far away, and then suddenly you will go back here. So this has the chance to be a rather stiff problem to study. Before going there, let's look at the trajectories that we study. We take a second order integrator. Here we have a very large type step. You can see what big jumps it does. When you start out behind the sphere or here, what happens? You go out, you get close to the sphere, and then you suddenly get through this attractive fixed point. And when you start inside, you have the similar motion. So you move inside and you go here. And when you start on the boundary, like the green curves, you go from the boundary toward this point. So you can see already that this integrator has trajectory that stay on the surface. And if you zoom in and rotate it, you see that the green line are really staying practically on the surface. You can compute exactly how these fixed points are moved, and many more stuff that I don't have time to get into. And then you see also this line, the point here very close that jumps, shoots up here, and the one here that shoots down. But what happens if we go a bit further away? Yeah, what happens is that, let me zoom in. If you take our variational or Hamiltonian integrator, you jump out, this little dot is our yellow sphere, you jump out to your large trip around and go back. But other integrators, even of higher order, are just not able to deal with it and explode. And it takes quite a while before you actually see that the two integrators start getting somewhere. And you see that when the time step is very, very small, the second order integrator for much larger time step was doing the right thing altogether. So the second order integrator, again, very near to the stiff point, behaves unbelievably well also compared to a fourth order integrator. And we believe this is due to the fact that we are adapting these integrators to the geometry of this system. And as a final test, I want to show you what happens if I integrate a different system. This is more in line with the linear drag. We have a Kepler problem with this oscillating type of drag. The reason we choose this is because this gives you some sort of like conservation of energy in average. And so you would expect your trajectory to not be exactly an ellipse, but to stay bounded in its oscillation. And you see that just as you would expect, Runge-Kutta has no chances there. At a certain point, it goes straight to the center and shoot out. But this contact integrator, second order or sixth order, stays there without any issue for a long time. You can go up to 300,000 and you wouldn't see any difference. And in fact, you see here, sixth order, the main difference between the second order and the sixth order is that the sixth order has nice conservation also of the momentum, while the second order includes a precession, which is also what you expect, but what happens even when you look at Kepler problem from the point of view of a symplectic integrator. So to recap and conclude, since the time is almost over, content mechanics allows us to describe a nice class of interesting systems. There are new systems coming from cosmology which might have actually quite intriguing property if they are investigated properly, both from the analytical and numerical point of view. And we believe that these families of contact integrators are actually good tool to explore these new kind of systems. We can argue that for systems that are close to symplectic, you can live with a symplectic integrator and use adiabatic theory to justify its properties. But when you are farther away from being symplectic, these integrators have proved over and over that they are actually quite robust and quite stable. So we believe that it's really worth to push forward this research, both in analytical terms and in the numerical terms, to see where it can go and what actually it can say, especially in these new systems in cosmology. Thank you very much for the attention. We have a bit of time still for questions.
Thank you very much, Marcello. So as you said, we have time for questions. And are there any questions from the author room in there?
No, not any. So
no questions. Okay.
Sorry. Yeah, you won.
Because I was thinking to my question.
Yeah. Please speak loud.
Which kind of model in cosmology you are thinking about?
Which kind of model in cosmology are you thinking about?
So the one that I was mentioning in the video, can you hear me actually?
Yeah.
The one that I was mentioning in the video is this class of contact Hamiltonian with quadratic dependence on the action that were discovered in this series of work by David Sloan when trying to study how to solve the problem of the attractor and how to solve the singularity at the Big Bang. So how to study what happens through the Big Bang by doing a scale reduction. So if you look at the Friedmann-Lebesgue equation, the Bianchi equation, there you have this parameter A that essentially is related to the Hubble constant and the scale invariance of the universe, and you can actually get rid of it. And this getting rid of it is the projection to the contact space that leads to these Hamiltonians. So mainly I was looking, Sorry?
Yeah, you're speaking about the scale factor.
Yeah.
Yeah, but it's a positive number. It's a positive variable. So the momentum, the conjugate momentum, is not a self-adjoint operator. It cannot have any self-adjoint extension. So, so the Schrödinger equation in that case is doubtful because you have to define properly the momentum operator.
Yeah, but I'm not talking about the Schrödinger equation there. I'm just talking about the...
About quantum cosmology. You are talking about the quantum cosmology. You are
No. I'm not talking about quantum system there. I'm just talking about the standard relativistic model.
Okay, thank you very much. We don't have so much time because we have to coordinate with the second room. So I suggest that the questions are between the people during the pause. We have a pause in 1 hour and a half, I think. Do you agree? Okay.
I can also answer in the chat if there are other questions,
Yeah,
no problem.
Sure, thank you very much.
Thank you, everyone. So Manuel, please ask Marcello in private message. Thank you, everyone. Thank you, Manolo. See you, everybody.